Here, we are to start with another playlist with still under advanced abstract algebra, and but this time we are going to focus on the concept of permutations, cosets, and direct products. And of course, you'll be touching significant and important concepts pertaining them. Let's start first with the idea of permutations of a set A. We have here set A containing elements 1, 2, and 3. And we are to list here all possible permutations. Now, permutations for this set is different from the idea of permutations pertaining to our arrangement of what they call this one, objects pertaining on statistics, because on the permutations for statistics, we do not necessarily need to list all elements. Say for example, if you have 3 elements and you are taking 2, just like this one here, 3 elements in set A and you're taking 2, so you could have 1 and 2, but you may not list 3, right? Because you're only picking 2 out of 3. But for the idea of abstract algebra, we are to, when I say permutations, it's bijective. It's both 1 to 1 and on 2. We are going to list it in this manner, okay? So our permutations generally will have in this form here. It would be written like this. And since you have 3 elements, 1, 2, and 3, they will be mapped to another element of the same set. So say for example 1, 2, and 3. This means that 1 is mapped to 1, 2 is mapped to 2, and 3 is mapped to 3. Notice that's only one element is mapped to the other because it's both bijective. It's 1 to 1 and on 2. And this is one of the first permutation that we could draw for this specific set A. This is actually considered as the identity permutation since the elements are just mapped to itself. And generally we call this, or we label this as row sub 0. That's our identity permutation. We can list the rest of the permutations of set A by considering the set as an equilateral triangle here. So you have your elements 1, 2, and 3. Again, the first permutation is the identity permutation where the elements are mapped to itself. The second permutation, we can call it row sub 1, is when we are going to rotate the vertices of this triangle. Say we're going to do it like this: rotation, rotate, rotate, rotate. That would mean the new plotting or new positions of our vertices would be, say for example here, this would be our 1 now, this would be our 3, this would be our 2. So what does this tell us? If we're going to look at each pairing, we have seen here that for this here, 1 is now mapped to 2. So 1, 2, 3 here as well. So 1 is now mapped to 2, 2 is now mapped to 3, and 3 is now mapped to 1. Okay, so this is now your second permutation. The third permutation you could do is, after rotating, you still rotate it another 1. Okay, you rotate it more. Therefore, you will have your 2 here, your 1 is now here, and your 3 is here. And as you can see, for the original, you have 1 and the 3. So this would be your row 2. You have 1, 2, 3. So 1 is now mapped to 3. 2 is now mapped to 1. Sorry, that's 1. And your 3 is now mapped to 2. Of course, if you're going to rotate it one more time, you would see that the vertices will just return to the original position. As this a 3 here, once you rotate it here, it will just return to 3. This 2 will just return to 2, and 1 will just return to 1. Hence, you'll have your identity permutation as mentioned earlier. So I already have these 3 permutations. The rest of the permutations can be determined like this. So let me go back to my equilateral triangle. You have 1, 2, 3. Okay. If we are going to come up with a certain what do you call this one, perpendicular bisector of each side. So say for example, the side opposite to 1, going to have it like that. Okay. Once I'm going to draw that imaginary line, and with that line, I'm going to fold our the triangle. That would mean that these two will just be mapping to each other, and 1 will just be retained as itself. This would be our mu sub 1, our fourth permutation. 1, 2, 3. Again, 1 is just 1 itself. 2 will be mapped to 3, and 3 will be mapped to 2. As you will fold this one here, you would see that this 3 will be placed here, this 2 will be placed here, and 1 will, sorry, that's 2, and 1 will still be here. So that's your mu permutation, mu sub 1. Okay, so let me continue here and use another color. What if I have the same triangle, 1, 2, 3, but instead of drawing or coming up with a perpendicular bisector to the other side from vertex 1, I'm going to have it from vertex 2. Okay, so with this, I'm going to fold it like that. So 2 will still be 2 here, 1 will be mapped here, and 3 will be mapped this one here. That would mean my next mu sub 2, 1, 2, 3. So 1 will be mapped to 3, 2 will be mapped to itself, and 3 will be mapped to 1. And lastly, of course, we still have one more perpendicular bisector, 1, 2, 3. That is from the vertex of 3. Okay, assuming it's a perpendicular bisector, once you flip that or fold it in that manner, 3 is still here, 2 is here, 1 is here. So your mu sub 3, 1, 2, 3 will be mapped. 1 is mapped to 2, 2 is mapped to 1, and 3 is mapped to 3. So these are the 6 permutations. There are only 6 permutations for a set containing 3 elements. Okay, so you will have the identity permutation. You have this first rotation, second rotation. They are called raw. Your mu would be for flipping using the perpendicular bisector. This here as well, and here as well. So these are your 6 permutations for your set A here. Now this is very important as we are going to look into permutations of another set containing 4 elements. That will be for the next video. Thank you very much for watching.